The talk is Minimax-Regret, Sample Selection in Randomized Experiments.
Thank you. So thanks everyone for staying up until the last talk. So today I want to talk about the Minimax-Regret sample selection in randomized experiments. This is joint work with Henry and Emma from Stanford Computer Science and also my wife. So let's start with what is sample selection and why we think it is important. So usually people run experiments because they want to learn about pros and cons of a new treatment of interest. They do that by simply participants from the population, randomizing treatment to those participants and then observing their outcome. And then based on the observed outcome, they will decide whether it's beneficial to assign treatment to population participants. And the question we're going to study today is how to sample participants from the population. If everyone in the population reacts the same to the treatment, then this question is trivial. We can just probably sample uniformly at random from the population. However, when there is treatment effect heterogeneity, meaning that different people might react differently to the same treatment, then this question is trickier. For example, consider COVID-19 vaccine trial that is stratified by age. Usually it is stratified by age because people do believe that participants in different age group will react differently to the vaccine. And in that case, how many individuals from each age group should be enrolled? We might expect the older group to benefit more from the vaccine, but they may also experience more serious adverse reactions. And there are potentially a lot of factors that you want to take into account, and the answer to this question is not that clear. Of course, now it's very abundant before, so those trials have a relevant value reality. What are people doing? As a case study, we looked at a phase 3 randomized placebo control study used to evaluate the efficacy and safety of an mRNA vaccine. In this study, about 30,000 participants are randomized to treatment and control in a 1-to-1 ratio. They consider 3 different strata for randomization. One as a younger, not at risk for severe COVID group. Second, a younger at-risk group, and finally, an older group. In their protocol, they wrote at least 25% of enrolled participants are not to exceed 40%, will be from the greater than or equal to 65 years age group and smaller than 65 years at-risk group. But they didn't really mention the reason behind those choices. It might be based on the conventional knowledge that you need to sample proportionally to proportion of those people in the population. Based on those numbers, it might be that case, or it might be based on some other common practices we don't know. And in fact, it is quite common that people just report those proportions without really giving a reason. The goal of this talk is then to develop a principled framework that allocates samples across heterogeneous groups. We hope that we can maximize social welfare and offer robustness against worst-case environment. And our approach is to balance costs and benefits through an explicit utility function. Throughout, we assume that we are running stratified completely randomized experiments. This is a two-step procedure that's commonly considered in clinical trials, such as that COVID exemplified earlier. So in this type of experiments, there are 2 steps. In the first step, participants are grouped in the strata according to their clinical features by the practitioners. And in the second step, they will randomize exactly half of participants in each group to treatment and half of them to control. We know that there's actually a long history on total sample size calculation and a large existing literature that gives guidelines on how many participants to enroll in an experiment in total. In such a well-established framework, researchers will often assume that there exists some data generating distribution from choice by a homogeneous treatment effect. And the total sample size is then chosen to be the smallest possible sample size, such that there is still statistically significant detection of the average treatment effect whenever this effect is larger than a practically relevant threshold determined by the practitioner. And that is, sorry. No, how is it?
Yeah.
Thank you so much. Thank you.
Sure.
And that is this A in the alternative hypothesis. This has almost become the standard running clinical trials. And in that earlier, in that whole example that I talked about earlier, although they don't explain reasons behind their choices of those proportions, they have a very long section talking about how they calculate their total size. However, recently there have been some works that revisited the sample size calculation problem, but with a different focus on welfare considerations. And there is this Minimax-Regret rule that is developed by Mansky and Hanov in a thread of works, showing that even relatively small sample sizes can still yield very strong welfare guarantees as compared to the sample size required in a power-based calculation. There's also another series of work that calculated total sample size using Bayesian rule based on prior information such as earlier phase trial and historical data set. However, we know that the question of whom to enroll has not received similar attention. As I mentioned earlier, one of our goals is to optimize the social welfare, but there can be potentially many different definitions of social welfares. In this work, we mainly consider two different definitions of welfares. The first one is a population average utility, or sometimes referred to as a utilitarian social welfare. So this is to simply calculate the aggregated utility for the population as a weighted average of the group-wise utilities, where this alpha G is a weighting parameter. We know that this utility function maximizes the overall welfare of the population. And if alpha G is something like the proportion of that group in the population, that ensures that everyone in the population is weighted equally in the calculation of overall welfare. Although this is perhaps the simplest and most common approach of calculating the social welfare, people have been arguing that maximization of this population average utility may sometimes result in decisions that prioritize the overall population's well-being at the expense of utility for minority groups. And this is especially the case if the treatment effect in the minority group is very different than the rest of the population. And in that case, we might assign a treatment rule that is not appropriate for that minority group to them. And if this is a concern, people will sometimes use this egalitarian social welfare, which is defined as the utility in the worst off group. In other words, we are focusing on maximizing utility uniformly across all groups or uniformly across all individuals in the population. Bringing insights from those utility functions, we build a utility-aware framework that can be used to guide sample selection. We consider a framework where there are in total capital G, a finite number of heterogeneous groups, each with its own treatment effectivity that can be arbitrarily different across groups and the same within groups. The main choice we're going to make is the appropriate sample size NG for each subgroup G to be included in the study, satisfying a budget constraint that there can be at most capital N units. And that's something we can calculate using those sample size calculation methods. Let's start with a workflow of decision-making using experimentation. So the data set we observe from the experiment is going to be determined by both an experiment design chosen by the decision maker and the data generating process chosen by the nature. The decision maker has no idea about the data generating process, especially something like the heterogeneous treatment effect, because that's something they want to learn from the experiment. However, they can design an experiment and use the collected data to learn about the effect and design policy. So after, and in this work, we will mainly focus on the sample selection design. So after they collect data, the decision maker will use an estimator of choice to estimate the treatment effect in those groups. And then based on that treatment effect, to design a treatment policy of whether they will administer treatment in the population for those groups or not. And then according to the quality of those treatment policies, they will obtain a utility function. And hopefully we will be able to find a sample selection that optimizes this utility. However, this utility is going to be a function of the data set. But when we are designing the experiment, we are at here, and we cannot really know what is data set. But something we can imagine is, you say like, if I use this sample selection, then for all possible realization of the data set, what is going to be my utility in the future on average? And that is the expected utility with expectation taken over the data generation. And our goal is to identify the optimal sample selection and optimize this expected utility subject to the budget constraint. But here another challenge is, since we don't really know what is data generating process, we also cannot calculate the expected utility when we are designing the experiment. And here we address this challenge by considering Minimax-Regret framework. In a Minimax-Regret framework, the DGP is assumed to be chosen by an adversary with knowledge of design and estimation choices. So we assume that this adversary can manipulate the heterogeneous treatment effect tau, the treatment effect in each of the groups. And the goal of this adversary is to make our decision as bad as possible. After collecting the data, we will then use a decision rule that maps the data to a G-dimensional binary vectors of decisions of whether we will administer treatment or not within each group in the population. In that work, for demonstration purposes, we consider a commonly used group-wide utility function, which is to define it as the difference in outcomes when we assign treatment according to the decision learned from the experiment and when we implement the baseline policy that just put everyone into control. And we start by considering the current social welfare and calculate the aggregated total utility as a weighted average of the group-wise utilities. Okay. Instead of optimizing the utility directly, we optimize regret, which is the difference between utility achieved by the oracle decision and the utility achieved by the decision made according to data observed from the experiment. It has been shown that optimizing regret has many desirable properties and is often less conservative than optimizing utility directly. And again, our goal is to find the sample selection that optimizes expected regret with expectation taken over data generation uniformly across all choices made by the adversary. And this will provide us some worst case guarantee against different environments. Just a quick definition of the Minimax-Regret sample selection. We say a sample selection is Minimax-Regret if the sample selection together with the decision rule minimizes the maximum expected regret when the treatment effect is chosen by an adversary. And we give an exact solution to this Minimax-Regret selection problem under a general class of DGPs when we run a stratified, completely randomized trial with a total sample size of n. We assume that the potential outcomes are ID observations from two normal distributions. Here, BG is a baseline parameter, tau G is the treatment of interest that we care about, and S0G and S1G are the noise levels in the observation. Just a few side notes. Here, we only allow the adversary to choose tau G, but if they have choice over those noise levels, we expect them to make them as large as possible. So they can also be regarded as upper bounds also on non-standard errors. And also, although we assume that those potential outcomes are normal distributed, we can actually relax this assumption to be from any subscription class, and our result will still hold in large samples. Recall that there are in total two choices we need to make. One is the sample selection and one is the decision rule. So here in the first step, we find the Minimax-Regret decision rule given any sample selection n. And we show that this decision rule induced by the threshold of the difference in means estimator is the Minimax-Regret decision rule. So what is this? This is simple to say that in each of the groups, I calculate the difference in means estimator and then assign treatment if it is greater than 0 and otherwise assign control. And since this is Minimax-Regret for all sample selection, the second step, we fix this decision rule and show that this following sample selection is Minimax-Regret. Recall that this alpha G is the weight we use in the utility function. So this is to say that compared with a proportional selection, this Minimax-Regret framework shrinks the selection towards an equal allocation. We find this rather surprising result because recall that in the utility function, we didn't really prioritize the minority group, but still, our results suggest that it's beneficial to oversample the minority groups and employ a sample selection that's proportional to alpha G to the power t-thirds. This is definitely not a common choice in the literature, and I haven't seen anyone using that, to be honest, but it might be something worth considering. The next question we ask is, if this is not a common choice, then what are the reasons behind those common choices? Is there setting where those widely adopted sample selection methods, such as proportional selection and equal selection, are also optimal? And the answer is yes, but we need to make some changes to the problem. The first variant we consider is a joint Minimax-Regret sample selection. This is the case where we restrict the decision space to be a decision class. Only a joint decision can be made for all groups, according to the sign of a pool difference means estimator. This is to say that we just take the entire sample and calculate difference means, and then we assign treatment to everyone in the population if it's greater than 0. And we say a sample selection and joint Minimax-Regret if the sample selection minimizes the maximum expected regret subject to this class of decision rules. And our result shows that proportional selection is actually joint Minimax-Regret. This is often a default choice when designing stratified experiments, but we show that it is only optimal in the minimax sense in this rather restricted setup. If the decision maker is allowed to make different decisions for different groups in the population, then this will no longer be optimal. Finally, we look at an egalitarian Minimax-Regret sample selection motivated by the egalitarian social welfare that I mentioned earlier at the beginning of the talk. So we say a sample selection to be egalitarian Minimax-Regret if this sample selection together with the decision rule minimizes the maximum expected regret in the worst off group. So this is the case when the regret objective is no longer framed in terms of average utility, but rather at the group level. And we hope to provide an upper bound on how the regret can get for everyone in this population. And this is the result in sample selection. Recall that those S0G and S1G are noise levels. So this indeed leads to an equal sample allocation for all groups if the noise levels are the same. And we know that it shares a common ground with the new allocation, which allocates sampling proportionally to the standard deviation, which is kind of like we sample more data if it's harder to learn about treatment effect in that group. In our paper, we also briefly talked about Bayes optimal sample selection, and we have a simulation comparing Bayes optimal sample selections with those Minimax-Regret sample selections. We found that surprisingly, those Minimax-Regret sample selections are not that conservative as one might think they are. They sometimes overlap with the Bayes optimal sample selection, especially in large sample cases when the sample size is chosen by the power analysis. And we also have a case study that replicate the COVID-19 vaccine trial I mentioned here. So I guess that concludes all I want to talk about today. And just to quickly summarize it, we propose a utility-based framework for sample allocation across groups. Under Minimax-Regret framework, we show that different combinations of decision paradigms and social welfare functions may lead to different sample selections. As opposed to saying that you have to follow our formula and select your sample, we think of it more of a working message saying that this is a question of worth investigating and there should not be a default choice such as proportional selection. And the optimal allocation depends on many factors, different beliefs and fairness considerations can result in very different allocations. Thank you.